December 9th, 2025, 6 a.m. Eastern Time, the European Space Agency releases an image that shouldn't exist, a supernova, 13 billion light-years away, captured by the James Webb Space Telescope. But here's what makes this extraordinary. When this star exploded, the universe was only 730 million years old, and yet this explosion, this death of a massive star at the edge of time itself, looks almost identical to supernovae we see today. That's the mystery. The laws of physics, the way stars die, the mechanics of cosmic destruction, they were already perfected when the universe was still an infant. How is that possible? Welcome back. For those of you who've been following Webb's discoveries since it launched in 2021, you know this telescope has rewritten the astronomy textbooks more times than we can count. Galaxies that formed too early, black holes that grew too fast, structures that shouldn't exist. But this one is different. This isn't just about finding something unexpected. This is about watching the universe's very first generation of massive stars meet their violent end. And the data Webb return tells us something profound about how stable, how unchanging, the fundamental rules of our cosmos really are. Let me take you back to March 14th, 2025. That's when it started. The SVOM satellite, that's the Space-Based Multi-Band Astronomical Variable Objects Monitor, a Franco-Chinese mission launched in 2024, detected a burst. Not just any burst, a long-duration gamma-ray burst. These are the most energetic explosions in the universe, more energy in 10 seconds than our sun will produce in its entire 10 billion-year lifetime. Within 90 minutes, NASA's Neil Gehrels Swift Observatory pinpointed the exact location. And here's where it gets interesting. The initial analysis suggested this wasn't coming from a nearby galaxy. This was coming from the edge of observable space. The team did something astronomers rarely do. They interrupted Webb's carefully planned observation schedule. This was urgent because gamma-ray bursts fade fast. If they wanted to catch what caused this explosion, they had 48 hours, maybe less. And what Webb saw when it turned its infrared eyes toward that distant point in the constellation, Leo, changed everything we thought we knew about the early universe. Dr. Andrew Levin, lead author from Radboud University in the Netherlands, said something remarkable in the press conference. Quote, "Only Webb could directly show that this light is from a supernova, a collapsing massive star." End quote. Think about what that means. Hubble couldn't do this. Ground telescopes couldn't do this. Only Webb's unprecedented infrared sensitivity could peer through 13 billion years of cosmic history and say definitively, yes, this was a supernova. They designated it SN in GRB 250314. The Z value, that's the redshift measurement, came in at 7.3. For context, a redshift of 7.3 means this light has been traveling toward us since the universe was 730 million years old. To put that in perspective, the first stars probably formed around 200 million years after the Big Bang. This supernova happened only 500 million years later. This is practically the dawn of time. But here's what stunned the research team. Dr. Antonio Martin Carrillo from University College Dublin said they made predictions based on local supernovae, the ones we see in our nearby cosmic neighborhood today. They expected the early universe supernova to look different. Strange composition, unusual light curve, something exotic. Instead, quote, "To our surprise, our model worked remarkably well. The observed supernova seems to match really well the death of stars we see regularly." End quote. Think about that. The universe at 5% of its current age, barely out of the dark ages, and stars were already dying according to the exact same rules they follow today. Which brings us to the question NASA isn't asking publicly, but every astronomer is thinking, what does this tell us about how stable reality actually is? Here's what makes this discovery so philosophically profound. When you and I were watching the Apollo missions in the late 60s and early 70s, we were watching humans explore a moon orbiting a star that formed 4.6 billion years ago. Our entire solar system, everything we know, emerged from a cloud of gas and dust that itself came from earlier generations of stars. This supernova Webb observed, it's from the first generation, or maybe the second. These are the stars that created the first heavy elements: carbon, oxygen, iron, everything that would eventually make rocky planets possible, everything that would eventually make life possible. We're looking at the cosmic assembly line that built the raw materials for existence itself. But the uniformity is what's haunting. The physics of stellar collapse, the mechanism of supernova explosions, the light signatures identical across 13 billion years of cosmic history. The laws of physics weren't evolving, they weren't stabilizing, they were already perfect. Dr. Levin's team is planning a second observation epoch in 1 to 2 years. By then, the supernova light will have faded by 2 magnitudes. That will allow them to completely characterize the host galaxy, confirm the supernova's exact contribution, and potentially detect the remnant left behind. If it's a neutron star or a black hole, Webb might be able to see it. Here's what NASA didn't emphasize in the press release but matters enormously. This was only possible because of rapid international coordination. SVOM detected the burst, Swift pinpointed the location, Webb interrupted its schedule, the European Space Agency's Mars orbiter contributed tracking data. Within 48 hours, dozens of telescopes across Earth and in space were watching this single point in the sky. That's not automatic. That's decades of infrastructure, protocols, trust between nations, the same architecture we'd need if something was ever heading toward us. This supernova wasn't a threat. It exploded 13 billion years ago. The light just reached us. But the coordination, the response time, the ability to mobilize humanity's most sophisticated instruments on short notice, that's the real story. Webb will continue monitoring this region. The host galaxy, barely visible in the current data, might reveal more about how galaxies formed in that early epoch. The supernova remnant, if it's detectable in 2 years, could tell us about the very first black holes. But I want to know what you think. We've now seen a supernova from when the universe was 730 million years old. Webb's previous record was 1.8 billion years. How far back can we actually see? Will Webb eventually capture the death of the very first stars, the so-called population 3 stars, that contained no heavy elements at all? And here's the philosophical question. Does it unsettle you or comfort you that the laws of physics have been this stable for 13 billion years? Write your thoughts in the comments. Until next time, keep looking up. The universe is older, stranger, and more consistent than we ever imagined.